Now, welcome back again. Let us solve another numerical problem. This one is really interesting. Engineering mechanics, problem set 2.6, solution to 2.85. We will have few more problems to finish 2.6. We have been using method of moments, that is the turning effect of a force about a given point to solve the different numerical problems. So let us begin. A bar AB of length L from A to B is a bar of length L. Is supported as shown in the figure. This figure is E as given in the book. At any point along the length. At any point along the length means it can be here, it can be here, it can be here, anywhere. A vertical load Q can be applied. This Q is applied at some point along the length of the rod AB. Determine the position of this load, means whether it should be here or here or here or here, for which the tensile force S in the cable BC is a cable, the tensile force S in that will be maximum, where Q should be applied along the length of the bar AB for the tensile force developed in the cable BC to be maximum. Now, very interesting. Don't think this is the midpoint of A and B. This point is not the midpoint of the A and B. We have to find out that. Where is that point? Given AB is equal to L from here to here, the length of the bar, to find the axial force S maximum in the cable BC. BC is a cable. Since it is a cable, like a thin wire, the tensile force will be along the cable. And if you consider point B, it will be to this side, and if you consider point C, it will be to this side. Let it be S. Let S is the tensile force in BC acting away from the point B. Now let us produce the direction of two forces and let's see where they meet. Let D is equal to the point where the line of action of S and Q meet. Now, if you produce this Q to this side, and S to this side, they will meet at some point. Let that point is equal to D. So I have redrawn the diagram. I don't look at this, it went slightly wrong. So here, this is the line of action of the tensile force developed in the cable S going to this side. The line of action of Q when produced to this side. Both they meet at point D. So we are left with another force, the reaction force at A, that is RA. So RA when produced must pass through the same point, because that was the conditions for equilibrium. They have to pass through the same point. So what extra thing I have drawn here? I have drawn a perpendicular here on the line BD, so that I can find out this perpendicular distance later on, that is AF. Then I have drawn again a perpendicular AE on the line of action of Q, so that I can later on find out the value of this perpendicular distance AE, which will be used for the force Q to find its moment about the point A. And this perpendicular distance AF will be later on used to find the moment of the axial force S about the point A. Now let this distance from here to here is equal to X, right? Now what is given? This angle is given as 15, this angle is given as 60 degree, as you can see in the original diagram. Now, so there are three forces, Q, S and RA. The load Q, the axial force developed in the cable BC. Now, look, what is interesting is, don't confuse this point C as this point D. Your C is below this, right? So, I have not drawn this bar. I have just produced the line of action of S and the line of action of Q to meet at a point D, which is other than the point C. So let us take the moment of these three forces about A as the moment center. Means let us find out what turning effect these three forces will have about the point A. Now RA is passing through the point A. So RA does not have a turning effect about point A because RA doesn't have a perpendicular distance from point A. Q, the line of action of Q has a perpendicular distance AE from the moment center A. The line of action of S has a perpendicular distance AF from the moment center A. So both Q and S will have turning effects only. So that is what I have explained. RA passes through A, so no perpendicular distance from A. Therefore, RA does not produce any moment about A. Q, we are left with Q and S. Q and S both have some perpendicular distance from point A as moment center. So as you can see, let me show you again. The line of action of Q from the point A is at this perpendicular distance AE. The line of action of S from the point A is at this perpendicular distance AF. So both Q and S will have turning effects about A. Due to Q, the turning effect will be clockwise. Due to S, the turning effect about A will be anti-clockwise. So if both are equal, then the system is in equilibrium. So Q has a perpendicular distance AE, S has a perpendicular distance AF. Sigma, sum of the moments about A should be 0. So Q times the perpendicular distance will be equal to S times the perpendicular distance. Now we have to find value of AE and value of AF. That is interesting to find out. Now look at the triangle AEC. Now in triangle AEC, since this angle is 60, this line and this line, they are parallel. Therefore, this angle will also be 60. So if you take cos of 60, it will be AE over AC, that is equal to X. So in triangle AEC, cos 60 will be AE over AC, AE over X. So you cross multiply, you get AE as X times cos 60. We'll put this in equation 1 here. Now look at the triangle AFB. Look at the triangle AFB. AFB, right angled here. So we are required to find AF. So if you take sine of 15, it will be perpendicular over hypotenuse, that is AF over AB. And the value of AB is taken as L. So in triangle AFB, sine 15 will be perpendicular over hypotenuse AF over L. So if you cross multiply, you get AF is equal to L sine 15. And AF is here in equation 1. Put this value of AF, that is equal to L sine 15 in equation 1. So now the equation 1 has been reduced to Q times X cos 60 is equal to S times L sine 15. So we are required to find out the value of S. We have taken this distance, unknown distance, as X, and this X will be found out for the maximum value of S. Now, so I keep S on one side. So I keep S, the axial force developed in the cable, on one side. So this L sine 15 comes to the left side, so is divided. Now look at this equation. Now is the argument. Now if X is equal to 0, then this numerator becomes 0. 0 by something is 0. So S is equal to 0. So the axial force is 0 when X is equal to 0. Means if this load Q is not applied here, is applied here, then X becomes 0. Then the axial force S developed in the cable BC will be minimum, that is 0. When this Q is applied here, means making X is equal to 0, then S is equal to 0, that is the axial force developed in the cable is minimum. But we are required to find the maximum value of S. So if you look at this is a fraction. So this is a constant, this is a constant, this is a constant, this is a constant, and X is in the numerator. So if X is maximum, then S will be maximum, and X can be maximum. If you look at the diagram, X will be the maximum value of X. X starts from here. So if this point is equal to here, then X is equal to maximum. So the maximum value of X is equal to L. So in this fraction, if X is equal to maximum, S will be maximum. So the maximum value of X is equal to L. Therefore, S will be maximum. Let it be represented as X max. So now put for X is equal to L. Put X is equal to L. So L cancels. So Q times cos 60 over sin 15 is equal to your maximum value of the axial force developed in the cable. Now put the values. This comes out to be 1.931 times the load Q that you are applying. So S will be maximum. Its value will be this much when X is equal to L. Means Q is applied. If this Q is applied at this end, here the value of S will be maximum. So I hope this was interesting to you, and if you really like the explanations, the way I explain, I have tried to explain for a common man with a basic knowledge of physics to make it out. Give a thumbs up, and you may like, you can subscribe also. Thank you.